With the example, we want to use the Lagrange multiplier to find the greatest and least value of the function that's f x y z is equal to x plus y plus z, subject to the condition x squared plus y squared plus z squared equal to 25. So actually we want to find 3 points, 3 values which are having the maximum value, the distance from this function and to the sphere to the maximum. That's actually the other way of saying this question. Sum of the 3 numbers, which is maximum with reference to the sphere. So we are having 2 functions. Our first function is when we want to find the solution. We write our 2 functions. One function is which we want to find the maximum minima. That's my sum of the numbers x, y, and z. This is x plus y plus z. And the constraint, the condition is my gxyz. My gxyz is x square plus y square plus z square. You know this equation. Minus 6 minus 25 is equal to 0. So this is not something new for you. You already know this one. This is the equation of a sphere. Minus 25 is equal to 0. Again, we have the same method, that Lagrange multiplier. The gradient of x is equal to gradient of g, and then we solve it to get our solution. So gradient of f is equal to 1, 1, 1 respect to x, y, z, and here we get here 2x, 2y, 2z, and multiply by lambda. So I can get here 3 equations. This is 1 is equal to 2 lambda x, and 1 is equal to 2 lambda y, and 1 is equal to 2 lambda z. And our constraint is gxyz equal to 0 is x square plus y square plus z square is equal to 25. We want to solve these 3 or 4 equations to get the value of x, y, z and the value of lambda. So here from the first 3 equations, I can find the value of x. My value of x is equal to 1 over 2 lambda. My value of y also is equal to 1 over 2 lambda. And value of z is equal to 1 over 2 lambda. I substitute these values in my condition and get here 1 over 4 lambda square x square, 1 over 4 lambda square y square, 1 over 4 lambda square z square is equal to 25. So when you just sum it, you get here 3 over 4 lambda square is equal to 25. Or we can say it here 100 lambda square is equal to 3. And my lambda square is equal to 3 over 100. And my lambda is equal to plus minus root of 3 over 10. So this is the value of lambda I got. Now from here I substitute the values for x, y, and z. I get the value of my x. My x is equal to 1 by 2. Lambda is plus minus root of 3 over 10, and that gives me here plus minus root of 3 over 5. Similarly, I get here y is equal to plus minus root of 3 over 5, and I get here my z. My z is equal to plus minus root of 3 over 5. The function, I get here the points, plus minus root of 3 over 5, plus minus root of 3 over 5, plus minus root of 3 over 5. If I expand them and try to write, I'll get here the points, many points here. Is root of 3 over 5, root of 3 over 5, root of 3 over 5. Then 1 is negative, both are positive, minus root of 3 over 5, minus root of 3 over 5, and root of 3 over 5. Then 2 are negative, we get 1 upon root of 3 over 5, minus root of 3 over 5, and root of 3 over 5. Then my second one is negative, I get here root of 3 over 5, minus root of 3 over 5, and root of 3 over 5, and so on. I go on like this one, and I can write here all are negative, root of 3 over 5, root of 3 over 5 with minus sign, minus root of 3 over 5. Now if I just imagine, because my fxyz is equal to the sum of these numbers, this is equal to x plus y plus z. If I take all the numbers as positive, I get the largest value, and all are negative, I get the least value. When any one of them is negative or positive, they are cancelled, and we are not having the least. So I take here the number, the value of the function here. This is a root of 3 over 5, root of 3 over 5, and root of 3 over 5, and that's equal to root of 3 over 5 plus root of 3 over 5 plus root of 3 over 5, and I get here 3 into root of 3 over 5. And then I can have the value, for example, I have this f of minus root of 3 over 5, root of 3 over 5, root of 3 over 5, and I substitute, I get here minus root of 3 over 5, plus root of 3 over 5, and plus root of 3 over 5. When I simplify this one, I get only root of 3 over 5, and so on. When I get here all the values negative, f of minus root of 3 over 5, and minus root of 3 over 5, and minus root of 3 over 5. So I'll get here minus root of 3 over 5, minus root of 3 over 5, and minus root of 3 over 5. So that gives me minus 3 into 3 root over 5. Now when I check all this one, this is the maximum value, this is the largest value, this here is maximum, and we having the smallest value, this is value is minimum, that is the smallest value, because we know the other values will be not on that as I've seen it, because when the all three are negative, that's the minimum, and when all the three are positive, that's the one idea I just gave. There can be many questions with reference to this one, that we can have different type of curves and we have different type of functions, and we find the maximum minimum value of that. When they solve calculations, we solve it, find the value of lambda, substitute it, find the value of x, y, and z, get the values, and then according to the condition we say is the largest value or smallest value. So we're having many examples in my notes, and I'm not able to do the all examples here on the video. I will recommend you that you just go to my notes, and given in the description the reference for that one. Just get the PDF file for that, and you can study more examples for that, because I'm just going to give you the last title of this one, that we're having the one function which you want to find the maximum minima, and subject to more than one condition. It can be two conditions, it can be three conditions, it can be four conditions, any number of conditions, but the idea will be the same. We can just, as we having here three variables and we solve it, we can have four variables. We can do it also for that one. So here also we can have one function and with many conditions. So I'm going to give you the idea for one function with two conditions. That's my next discussion. And as I told you that for the new videos, you must subscribe the channel and press the bell icon so to get the notification for that one. Thank you for watching, and I'm going to give you one more example. We want to discuss the, as I mentioned, the Lagrange multiplier function subject to more than one condition. We want to find the maximum minima of the function f x, y, z, and a condition subject to the constraint is g x, y, z equal to 0 and h x, y, z equal to 0. We define two Lagrange multiplier, lambda and mu, and we write this equation with the gradients. Gradient of f is equal to lambda times gradient of g plus mu times gradient of h. Now we can have the gradient of f, this equal to my f of x, f of y, f of z, and equal to lambda times gradient of g, that's g of x, g of y, and g of z. Meantime, we are having here h of x, h of y, and h of z. Now when I write my equation, if the vectors are equal, I can write here my three equations. F of x is equal to lambda times g of x plus mu times h of x. So my f of y is equal to lambda times g of y plus mu times h of y. And I can have here my f of z. My f of z is equal to lambda times g of z plus mu times h of z. Now we have three variables x, y, and z. Also we have the constants Lagrange multiplier lambda and mu. This means we need five equations. So this is my equation 1, this is my equation 2, and this is my equation 3. I take the condition g, x, y, z equal to 0. This is my equation 4. And I take h, x, y, z equal to 0. This is my equation 5. So as before, we solve this equation and find the value of x, y, z, lambda and mu, and then we find the function at x, y, z values. The largest value is maximum and smallest value is minimum. So I give you an example and explain you this method with the example. I'm going to give the example where we are going to discuss the Lagrange multiplier. We have the function and the subject to more than one constraint. It can be two constraints or three constraints. As I discussed above, that we're going to take two constraints in this case. So we have the function that's giving the temperature distribution at any point of the sphere. Temperature is 20 plus 2x plus 2y plus z square, and sphere is x square plus y square plus z square equal to 11. And it's being intersected by a plane x plus y plus z equal to 3. The temperature distribution, we find the gradient and Tx, derivative with respect to x, taking y and z a constant, we get 2. And we have gradient of respect to y, derivative with respect to y, partial derivative, taking y, x and z as constant, get here 2. And then the derivative with respect to z, partial derivative, taking x and y constant, get 2z. Similarly, for the gradient on the sphere x square plus y square plus z square 11, the gradient will be g of x, g of y, g of z. G of x is 2x, g of y is 2y, g of z is 2z. Then mu time gradient of h, we are having x plus y plus z minus 3 equal to 0. So gradient will be 1, 1, and 1. So we get here this equation, and this is our vector equation. Two sides are equal, so each component is equal. So we get here three equations. 2 is equal to 2 lambda x plus mu, and 2 is equal to lambda y plus mu, and 2z is equal to 2 lambda z plus mu. We have three unknowns. We have the unknowns are x, y, z, lambda, and mu. We need 5 equations to get the solution. So we have three equations we get from the gradient from the Lagrange multiplier vector. Now we have two equations that give us from the constraints. The first constraint is the sphere, x square plus y square plus z square minus 11 equal to 0, and second is x plus y plus z minus 3 equal to 0. That's my gxy, z, and hxyz. So get here 5 equations. We want to solve this 5 equation, and then we can find the value of lambda, mu, x, y, and z. We neglect the value of lambda and mu and get the value of x, y, and z. That give me the extreme points. So we get here, just writing it, from equation 1 and 2, we subtract it, we get here 2 lambda into x minus y equal to 0. So either lambda equal to 0 or x minus y equal to 0. We take lambda equal to 0. When we solve that equation, when you solve it, we get the critical points over 3, 1, minus 1 and 1, and minus 1, 3 and 1. You can do this mathematical, arithmetical work to find the point. Now we take the second one, the x equal to y. So we get here, because x is equal to y, so we get a point 1 by 3, 3 plus minus 2 into root of 3. And when we substitute, we find the value of z. Z is equal to 1 by 3, 3 minus plus root of 4 into root of 3. So we have here these critical points, two critical points when lambda equal to 0 and two critical points when lambda not equal to 0. We find the value of the function at these critical points. So we get here 25 and 91 by 3. So the 25 is the minimum value and 91.3 is maximum value. Say T is equal to the temperature at this point is equal to 25, the minimum temperature. At the point 3, 1, minus 1 and 1 and 1, 3 and 1. And is a maximum temperature 30 and 0.33. That's on the point when we take lambda equal to 0. So this is the idea that we can use, even you can use more than two constraints. We can get here three constraints, and we can find the maximum minima with reference to three constraints using our Lagrange multiplier. So we have taken the example with one constraint, with two constraints, and with three constraints. With this, we come to end of this chapter. So always, as I said, we're having the notes in the description. You can take the notes from the description. You can just subscribe it, that we're having more examples and more things we are coming for mathematics. You're able to reach it. And this completes this chapter. Thank you very much.